I'm Dick Gallagher of the SEDCO training staff, and during this first session we'll be discussing stability. Stability is the tendency of a vessel to return to its original upright position after it has been tilted or heeled by an external force, such as a wave. A vessel that is top-heavy is said to be tender or cranky. It has a slow roll and a weak tendency to return to its original upright position. Here, the stability is considered to be poor. A vessel with most of its weight located towards the bottom of the vessel is said to be stiff. Its roll is quick, and it has a pronounced tendency to return to the erect position without much roll. This vessel is said to have excessive stability. Our goal is to have an easy rolling period on a ship. Let me point out here that we are talking about a ship and not a semi-submersible. On a semi-submersible, we want a tender or cranky vessel so that the roll is very slow and manageable to avoid problems with the drill string. We'll talk more about this later, but for right now we will be limiting our discussions to ships. We can determine the stability of a vessel by locating 2 points in the vessel: the center of gravity and the center of buoyancy. The center of gravity, what we will call G, is the center of mass of the vessel. It is at that point that all of the vertically downward forces of weight seem to act. If the vessel has a natural tendency to sit perfectly upright, in other words, if it has no list or imbalance, the center of gravity, or G, will be somewhere along the center line of the vessel. The center of buoyancy, which we will call B, is that point where all of the vertically upward forces of support, or buoyancy, seem to act. It is the center of volume of that part of the vessel that is below the waterline. So, gravity is a downward force, and buoyancy is an upward force. The displacement of a vessel is the weight of water that the vessel pushes aside or displaces when it is floated in water. Let's take a look. Here we have a tank that, as you can see, has been filled to capacity with water, so that if an object is placed in the tank, some water will be pushed aside or displaced and will be collected in the beaker. We're going to take a block of wood, which will symbolize a vessel, and float it in the tank. As you can see, the vessel pushes aside or displaces a certain volume of water. When we have collected the water in the beaker, we will weigh the water, and we will also weigh the block. When we compare the two weights, we will see that the weight of the displaced water is equal to the weight of the object. Well, it looks as if we've collected all the water we're going to get, so we'll just go ahead and weigh the block of wood. And we can see that the weight of the displaced water is equal to the weight of the object. K is the symbol used to denote the vessel's keel. The keel is the main fore and aft member of a ship's frame. It connects the bow with the stern. The keel is also a good reference point for measuring heights. When the vessel is in a stable position, the keel, K, center of gravity, G, and center of buoyancy, B, will be in a straight vertical line. The forces of buoyancy and gravity will be acting in opposite directions and along the same vertical line. Since the amount of force being exerted by both gravity and buoyancy are equal, the vessel will rest. When a vessel is tilted due to an external force, such as a wave, G, the center of gravity, will remain fixed unless the cargo within the vessel is free to move about. B, however, the center of buoyancy, will move because it is the center of volume of the immersed portion of the vessel. B will move towards the low side of the vessel. We call this new location of the center of buoyancy B2 to distinguish it from B1, the original location of the center of buoyancy. It is this movement of B that gives the vessel its tendency to return to its original upright position instead of turning over. This tendency to return is caused by what we call a couple, which is created by the opposing forces of gravity and buoyancy. A couple is formed whenever two equal forces are acting upon the vessel in opposite directions and along parallel lines. It's expressed as a certain force, in this case the opposing forces of gravity and buoyancy, times a distance, and here it's the distance between the lines of force. The result is what we call a couple or a moment. We can all recall examples of couples that we see and use every day. When we use a wrench, we are setting up a couple which causes the nut to rotate. Also, when we use a valve wheel or a steering wheel on a car, we are also creating a couple. As we said earlier, when the vessel is heeled or tilted by a wave, B will move towards the low side. It will move along the arc of a circle. The center of this circle is where the vertical line through B2 intersects the center line of the vessel. We will call this point the Metacenter, and we will abbreviate it as M. We'll talk a little more about M later on in the program. As we can see here, the force of gravity works downwards through point G, the center of gravity, and the force of buoyancy works upwards through B, the center of buoyancy. Because these 2 points are separated, a couple is created, which in this case will cause the vessel to return to its original upright position. In our diagram, the arm of our couple is called GZ. We already know where G is, so in order to find Z, we simply draw a line through G and perpendicular to the line of action through B2. GZ is called the arm of the couple. Here, GZ is called the righting arm, since it tends to make the vessel right itself. If GZ tended to upset the vessel instead of right it, it would be referred to as an upsetting arm. Moments also are described as either righting moments or upsetting moments. As we talked about earlier, a couple is expressed as a certain force times a distance, or a moment. In the case of a vessel that has been inclined or tilted, the moment or couple is expressed as the weight of the vessel, its displacement, times GZ. In the case of a vessel, this moment will be measured in foot-tons. It should be apparent that the greater the weight or displacement, the greater the moment, either a righting moment or an upsetting moment. Also, the greater the distance between G and Z, the greater the righting or upsetting moment. So, displacement times GZ equals righting moment. So far, we have been concerned with transverse stability only. This is the stability of a ship from port to starboard or from side to side. As you know, the port side is the left-hand side of the vessel when looking towards the bow, and the starboard side is the right-hand side of the vessel when looking towards the bow. Right now, we will not worry about longitudinal stability or a vessel's stability from bow to stern until we get into the subject of trim. As I said earlier, M is located at the intersection of a vertical line through B2 and the center line of the vessel. M is the highest point to which G can rise and still permit the vessel to have positive stability. It is called the transverse metacenter and is abbreviated as M. Let's talk about the equilibrium of a vessel for a minute. Equilibrium can best be described as one of three conditions: stable equilibrium, neutral equilibrium, or unstable equilibrium. First is stable equilibrium. This is positive stability, or a definite tendency of a vessel to return to an upright position at small angles of heel or tilt. Here, point M is higher than point G. This allows a riding moment to be set up when the vessel is tilted. This causes the vessel to return to its original upright position. Next is neutral equilibrium, where M and G are at the same point. There is no moment since there is no GZ. And there is no tendency of the vessel to return to its original upright position. There is also no tendency for the vessel to tilt any further. Unless another outside force is exerted on the vessel, it will remain in this heeled position. Finally, we have unstable equilibrium, where G is higher than M. Here, there is an upsetting arm, and the vessel will have a tendency to continue to tilt. So far, we have only discussed initial stability. This deals with what the vessel will do at small angles of tilt or heel of not more than 10 to 15 degrees. When a vessel is inclined more than 10 to 15 degrees, there are other considerations which we will look into later. As we can see, the greater the distance between G and M, the greater will be the distance between G and Z. And the greater will be the riding moment, or upsetting moment if we have the occasion with an upsetting moment. This distance from G to M is called metacentric height. It is this distance from G to M that determines the initial stability of the vessel. To find GM, we first have to measure KM. KM is the line between the keel and the metacenter. We determine where the metacenter is from the hydrostatic curves. As you learned in the study guide, the hydrostatic curves are a series of curves in the form of a graph which set forth the value of certain properties of a vessel involving the underwater form of that particular vessel. We will learn how to use the hydrostatic curves in the next program. For now, just remember that you will have to use the hydrostatic curves in order to locate M. Once we have found Km, we will have to calculate where G is in order to figure out Kg. Then we subtract Kg from Km, and we get Gm, the distance between the center of gravity and the metacenter. Before we actually find G, let's take a brief look at the theory of moments. We're all familiar with how a seesaw works. Well, the theory of moments works about the same way. From our playground experiences, we know that if two children, weighing the same, sit on opposite ends of a seesaw, the same distance from the center, or fulcrum, the seesaw will balance. This is because the moments on one side of the seesaw are equal to the moments on the other side. Here, let's take a look. We'll use G to indicate the fulcrum or balance point of the seesaw. In this example, we'll use 1 pound weights to represent 100 pounds, and 1 inch along the seesaw will represent 1 foot. So we'll place a 100-pound weight on the left side of the seesaw at about 10 feet from the fulcrum. The moments of this weight about the fulcrum are 100 pounds times 10 feet, or 1,000 foot-pounds. We will also place a 100-pound weight on the right side of the fulcrum at a distance of 10 feet from the fulcrum. The moments here are also 100 pounds times 10 feet, or 1,000 foot-pounds. Since the moments on the left are equal to the moments on the right, the seesaw will balance. Okay, now if we increase the weight on the right side of the seesaw, it will be thrown out of balance unless we move that increased weight in the direction of the fulcrum. Through a simple calculation, we can determine the exact location where the heavier weight should be placed in order to balance the seesaw. Let's assume that the weight on the right side of the seesaw is increased to 200 pounds. How far from the fulcrum should the 200-pound weight be moved in order to balance the seesaw? We know that in order to balance the seesaw, the moments on the left side have to be equal to the moments on the right. Since the moments on the left are 1,000 foot-pounds, the moments on the right also have to be 1,000 foot-pounds. So to find out the distance that we need to move the 200-pound weight from the fulcrum, we will simply divide 1,000 foot-pounds by 200 pounds of weight to get 5 feet. So we move the 200-pound weight 5 feet from the fulcrum, and the seesaw balances. A variation of the seesaw problem is a situation where we have a movable fulcrum, G, and fixed weights. Here we have a 100-pound weight 10 feet to the right of point A, and also 10 feet to the left of the fulcrum. A 200-pound weight is placed 10 feet to the right of the fulcrum. How far will the fulcrum have to be moved in order to balance the seesaw? Since the fulcrum is going to be moved, we cannot calculate the moments about point G unless we use algebra. So we will have to calculate about some other point. We'll use point A. In order to calculate the moments of the 100-pound weight about point A, we multiply 100 pounds times 10 feet, which is the distance of the 100-pound weight from point A, and we get 1,000 foot-pounds. In order to calculate the moments of the 200-pound weight about point A, we multiply 200 pounds times 30 feet, which is the distance of the 200-pound weight from point A, and we get 6,000 foot-pounds. Now we can find the distance that G must be from point A if we divide the total moments by the total weights. Total moments are 7,000 foot-pounds. Total weights are 300 pounds. Therefore, 7,000 foot-pounds divided by 300 pounds equals 23.3 feet. This is the distance that G should be placed from point A in order to balance the seesaw. So, if we move G 3.3 feet to the right, the seesaw will balance. This process will help us to find the height of the center of gravity of a vessel, or the distance from the keel to the center of gravity, kg, after a vessel has been loaded or unloaded or taken on fuel, and thereby change the height of G above the keel. It is important to remember that every piece of cargo or equipment has its own center of gravity, and that when any item is loaded or unloaded, this will have some effect on the kg of the vessel. To find the kg of a vessel, we will use the same theory of moments we just talked about, and we will imagine that the vessel is a vertical seesaw. Okay, we've covered a lot of ground up to this point, so let's take a coffee break. This will give you an opportunity to look over your notes, and then we'll meet back here in a few minutes. Okay, now we'll get back to where we left off. If you recall, we stated that we were going to find the kg of a vessel by using the same theory of moments that we talked about with the seesaw. We were going to imagine that the vessel is a vertical seesaw. Now our next step will be to calculate the moments about the keel, or K. Here's the formula that we're going to use. Kg, or the height of the center of gravity after loading or unloading, is equal to the final moments divided by the final displacement. Now let's go over the steps in finding kg after loading or discharging cargo. First, we will have to find out what kg is for the light or empty ship from the ship's plans. Second, we will have to estimate the centers of gravity for each item of fuel, cargo, stores, and so on. Third, we will multiply each weight by the height of its g above the keel. Fourth, we will add these moments together and add the moments for the light ship. The moments for the light ship are equal to the light or unloaded displacement times the light or unloaded kg. Fifth, we will divide by total weights, including the weight of the light ship. Let's work a few of these out. In our first problem, a vessel floating at its light draft or empty displaces 10,000 tons. The vertical center of gravity of the vessel, or VCG, is 20 feet above the keel. The VCG of the vessel is nothing more than the kg of the vessel at that particular stage of loading. If 300 tons of cargo are loaded 10 feet above the keel, and 200 tons of cargo are loaded 25 feet above the keel, what will be the new position of the center of gravity, or kg? In order to solve the problem, we'll use the formula we mentioned earlier. Kg is equal to final moments divided by final displacement. The final displacement is equal to the light ship, which is 10,000 tons, plus the cargo, which is 500 tons. This is a total of 10,500 tons. To find the final moments, we add all the moments together, including the moments for the light ship. The moments for the light ship are 10,000 tons times 20 feet, or 200,000 foot-tons. The moments for the 300 tons of cargo are 300 tons times 10 feet, or 3,000 foot-tons. The moments for the 200 tons of cargo are 200 tons times 25 feet, or 5,000 foot-tons. So the final moments are 200,000 foot-tons plus 3,000 foot-tons plus 5,000 foot-tons, which gives us a total of 208,000 foot-tons. Now, we divide the final moments, 208,000 foot-tons, by the final displacement, 10,500 tons, and we get a new kg of 19.81 feet. It is important to note that the height of the center of gravity has not changed much at all. This is because of the relative bulk of the vessel, which is 10,000 tons, as compared to the cargo, which is a mere 500 tons. In our second problem, we'll remove weight and then determine the vertical center of gravity of the vessel, the kg. Let's assume that another vessel has a kg of 25 feet and that the vessel and its cargo displace 15,700 tons. If 3 items of cargo have VCGs as shown here, and we remove them from the vessel, what will be the new kg? To solve this problem, we'll use the same method as we used with the first problem, except that we will be removing weight this time. Since we are reducing the displacement by removing cargo, we will be decreasing the total moments. Here's the formula, same as before. kg equals final moments divided by final displacement. To figure the final moments, we'll simply subtract the moments for the removed cargo from the moments for the vessel and all of her cargo. The moments for the vessel, as we know, are 392,500 foot-tons, which is figured by multiplying 15,700 tons times 25 feet. The moments for the removed cargo are calculated like this: 200 tons times 5 feet, or 1,000 foot-tons. 100 tons times 15 feet, or 1,500 foot-tons. 400 tons times 10 feet, or 4,000 tons. The total moments for the removed cargo are 6,500 foot-tons. We subtract this from the moments for the vessel, 392,500 foot-tons, and we get 386,000 foot-tons, which are the final moments. The final displacement is found by subtracting the weight of the removed cargo from the initial displacement, or in other words, 15,700 tons minus 200 tons minus 400 tons minus 100 tons, which gives us 15,000 tons. Now, if we divide 386,000 foot-tons, the final moments, by 15,000 tons, the final displacement, we get 25.733 feet, which is the new kg. If we look back at these two problems, we should be able to make a few rules which will show the effect on G when we load or unload cargo. First, if we load above G, we're going to raise G. Second, if we load cargo below G, we're going to lower G. And third, if we unload cargo from above G, we're going to lower G. Finally, if we unload cargo from below G, we're going to raise G.